So far we have seen how to calculate the parameters of a transmission line. The parameters means the inductance and the capacitance of the transmission line. Now from the cross-sectional area or all the physical parameters of the transmission line or the conductors used in the transmission line, the resistance can also be calculated. So once we get the values of the resistance, inductance and capacitance, we can actually represent a transmission line in terms of these parameters, and that is what is meant by modeling of a transmission line. And depending upon the length of the transmission line, we have seen that the transmission line can be categorized as short transmission line, medium transmission line and long transmission line. We have seen that if the distance is or the length of the transmission line is up to say 80 kilometers, it is considered as a short transmission line. And in case of short transmission line, we'll be neglecting the capacitance between the transmission line and the earths. But in other two categories, the medium length transmission line or medium transmission line and the long transmission line, we have to consider the capacitance as well. In case of short transmission line, we'll be considering only the resistance and the inductance. In case of medium transmission line, actually we can represent the transmission line as a pi representation or t representation. And let us see how to represent the transmission line. Before we start the discussion on the modeling of the transmission line, let us see what is the efficiency, how to define the efficiency of transmission line. And the efficiency of a transmission line, like any other electrical equipment or like any other electrical apparatus, the efficiency is given by the useful power output divided by the ratio between the useful power output and the power input. For example, in case of a motor, the power output will be the useful mechanical power output, and the power input will be the actual power drawn from the system. So the ratio between this, the output power and the input power, will give the efficiency. Similar is the case with the transmission line also. The efficiency of transmission line is defined as percentage efficiency, which is given by power delivered at the receiving end. You can see that when power delivered at the receiving end divided by the power sent from the sending end into 100, if you are representing that in terms of a percentage. And you can see that when some quantity of power is to be transmitted over the transmission line, invariably there will be some I square R loss. Power will be lost depending upon the physical properties of the transmission line or the conductor used. So if there is a higher dissipation, means more power will be dissipated on the transmission line. That means the more losses will be there and the efficiency will be getting reduced. So from this formula you can see that power delivered at the receiving end, if the same power sent from the sending end is received at the receiving end, the efficiency will be 100%. But practically always it will be less than 100%. And it can also be represented as power delivered at the receiving end into 100 divided by the power delivered at the receiving end plus losses. Here you can see that power delivered at the receiving end plus losses will give the power sent from the sending end of the transmission line. The regulation of a transmission line is defined as the change in the receiving end voltage expressed in percentage of the full load voltage. That is actually the rated voltage from no load to full load. That is the change in receiving end voltage from no load to full load. You can see this difference. When the transmission line is on full load, it will have some terminal voltage, and when that load is fully removed, or the load is, or when the transmission line is on no load, the terminal voltage will be different. So this difference expressed as a percentage of the full load voltage is known as the percentage regulation. So it can be defined as VR dash minus VR by VR. VR dash is the receiving end voltage under no load and no load condition, and VR is the receiving end voltage under full load condition. And you can see that VR dash and VR are the magnitudes of the voltages, and actually you will be considering the RMS value of the voltages when the transmission line is delivering full load and when the transmission line is on no load. And depending upon the line parameters and the length of the transmission line, sometimes most of the cases, if the inductance of the transmission line is predominating, the receiving end voltage will be always less than the sending end voltage. But in some special cases, as in the case of lightly loaded long transmission lines, sometimes the receiving end voltage will be higher than the sending end voltage, and that is known as the Faraday effect, which we will be discussing in the at the end of this discussion. As we have seen in the previous classes, the classification of the transmission line based on their length is, one is the short transmission line. If the line is up to, or the length of the line is up to 80 kilometers, in that case we will be representing the transmission line as a lumped impedance in terms of its resistance and inductance, and we will be completely neglecting the line capacitance. Here in this example you can see that this is the source impedances and this is the transmission line impedance. So this is actually the representation of the transmission line, and we are not considering any in this ZL is the impedance of the transmission line, and you can see that in this ZL we will be neglecting the capacitance, because if you compare the line parameters in case of short, medium and long transmission lines, the effect of the capacitance in case of short transmission line, it will be lesser or it can be negligible. That is why such a simple representation of the transmission line is possible. And in case of medium transmission line, the lines between, if the length of the transmission line is between 80 and 160 kilometers, the category or the categorization is medium length transmission lines. And you can see that sometimes the transmission line with length up to 100 kilometers can be considered as a short transmission line, and sometimes and actually this 160 kilometer, it is not a hard and fast rule. Sometimes there will be some approximations, or sometimes for the ease of analysis we will be considering a transmission line say up to 90 kilometers a short transmission line. So approximately it will be from 80 to 160 kilometers, and if the length is falling in between this range, so generally it can be taken as it can be considered as medium transmission line if the length of the transmission line is between 80 and 160 kilometers. In that case you have to consider the line capacitance also when you represent the transmission line in terms of its parameters. Here you can see that in case of a medium transmission line, two types of representations are there. Nominal T representation. Here you can see that this representation, it resembles the letter T in English. That is why it is known as the nominal T representation. And in this representation, second one, you can see that it is of the form of pi. That is why it is known as the nominal pi representation. And in case of nominal T representation, you can see that the whole capacitance of the transmission line for the whole length. Here you can see that, for example, if you are considering a transmission line of length say 160 kilometers or 150 kilometers, for example, using the formula what we have already discussed, you can calculate the capacitance of the transmission line, and we will be considering that capacitance. Actually you can see that the capacitance is the capacitance is distributed uniformly along the length of the transmission line, but for the ease of analysis we will be considering capacitance of the transmission line as a lumped capacitance, lumped at the center of the at the middle of the transmission line. Here we can see that the whole capacitance of the transmission line. Here this is the whole capacitance of the transmission line in terms of its impedance or admittance, and reactance or admittance. So you can see that we are considering that capacitance or the reactance of the contributed by that capacitance as a lumped element at the center of the transmission line, and half of the other parameters. Here you can see that the resistance of the transmission line is R, and the reactance or the inductive reactance of the transmission line is X, and so half of the line impedance is considered to be lumped at the starting of the transmission line, and half will be represented at the ending position of the after the capacitance. Here you can see that half of the inductance, half of the resistance plus the inductive reactance is considered to be lumped at before the capacitance C. And you can see that in this nominal T representation, half of the inductance and inductive reactance and resistance is lumped at this point, and after the capacitance, half of the resistance and the inductive reactance is lumped at this point. So it's something like it resembles the letter T in English. That is why it is known as the nominal T representation. So this is the nominal T representation of the transmission line. And in case of nominal pi representation, the whole the capacitance or the capacitive reactance is assumed to be lumped at the end, both ends of the transmission line. That means half of the capacitive reactance will be lumped at the starting point or the source end and the or sending end of the transmission line, and half of the capacitive reactance will be lumped at the receiving end of the transmission line, and the whole resistance as well as the inductive reactance will be lumped at the middle of the transmission line. So this will be the nominal pi representation of the transmission line. And you can see that we have seen that the capacitive reactance is given by omega c is equal to, or xc is equal to 1 by omega c. So this is xc in terms of ohm, or it will be in reactance. If you are representing that as admittance, so it can be represented as yc, and it will be the reciprocal of the reactance. So yc is 1 by xc, and that is given by omega c, where omega is given by 2 pi f, which will be depending upon the frequency of the transmission line or the frequency of the AC voltage, and the c is the capacitance of the transmission line. So yc, or the capacitive admittance yc, is given by omega c. And we know that if you have a voltage source if you have a capacitive reactance connected across a voltage source, the current through that will be given by V by Xc. So if you have to calculate so if you consider a circuit like this, if this is Xc, the capacitive reactance, and the voltage source is connected like this, so this is the voltage source, so the current IC will be given by Vs by Xc. But if you are representing the capacitive reactance, or instead of representing the capacitance in terms of its reactance, it can be represented in terms of its admittance. So in that case, the current IC will be given by Vs into 1 by Xc is Yc. So and it can be represented as a product of the voltage and the admittance, and it will be easy to calculate the current. And you can see that always this capacitance will be a shunt element. That is why it is represented as Ys here. In most of the books you can see it as Ys, or you can represent it as Yc, and it is given by j omega c. And you can see that if you consider the Xc, generally Xc, the capacitive reactance, is represented as minus jXc if you are representing the parameters in real plus imaginary form. And here in case of inductive reactance, you will be representing XL as jXL. And similarly in this line, you will be representing Xc as minus jXc. So if you consider 1 by Xc, that is equal to Yc, that will be 1 by minus jXc, and minus jXc will be 1 by minus jXc. Here you can see that 1 is minus j square divided by minus jXc. So it will be j, and 1 by xc is Yc, so it will be Yc. That is how you are getting the shunt element in this representation as Y is equal to jXc. Similarly, here you can see that in case of nominal T representation, we will be considering the capacitance of the transmission line as lumped at both ends of the transmission line by considering half of the total capacitance. So here you have Y by 2, half of the admittance will be considered to be lumped at the sending end, and half will be lumped at the receiving end. So this will be the T representation. And for line lengths more than 160 kilometers, the parameters are distributed. Actually, in all these cases, they are distributed uniformly along the transmission line from the sending end to the receiving end. But for the ease of analysis, we will be considering like this. We will be here in these cases. In case of short transmission line, actually we are neglecting the capacitance in order to simplify the calculations. But in case of and in that case, if you are neglecting some parameters, or if you are approximating some, or if you are approximating some parameters, actually it will be introducing some errors. But there the errors, if the length of the transmission line is less, or in case of short transmission line, the error introduced will be lesser. And in case of a medium transmission line, we have to consider the line capacitance. And here also you can see that by considering these representations, actually we are introducing some errors, but all up to up to these lengths 80 to 160 kilometers, the error introduced compared with the actual or the distributed parameters, it will be lesser or it will be acceptable. And for line lengths greater than 160 kilometers or say 200 kilometers, you have to consider the continuous distribution or the continuous variation of the line parameters, the inductance and the capacitance. You have to do rigorous calculations in order to assess the performance and efficiency of the transmission line. And as we have seen, sometimes if the length of the transmission line is up to 250 kilometers, you can consider nominal T and pi representations for the analysis of the transmission lines. But generally, for the transmission line whose length is greater than 160 kilometers, it is considered as a long transmission line. Now let us see how we can analyze the short transmission, or how we can represent a transmission line in terms of its electrical parameters. First, we will consider the short transmission line, and we have seen that in case of short transmission line, we will be neglecting the line capacitance. So in the calculations or in the phasor representation or in the analysis, we will be considering only the resistance and the inductive reactions of the transmission line. That means only the resistance and the inductance of the transmission line will be considered. So the representation will be here, because we don't have any shunt element, because shunt element, the capacitance will be a shunt element, because the capacitance is between the transmission line and the earth, or in between the lines. So in case of short transmission line, we will be completely neglecting the line capacitance. That means all the parameters or the variables will be considered as vectors or phasors. So Vs is the source voltage in its phasor representation, and Vr is the receiving end voltage. And you can see that the receiving end voltage, and you can consider this as a simple electrical network, and if you apply Kirchhoff's voltage law to this loop, here you can see that at some instant, let this point be positive with respect to this, and at the same time you have this as the positive at some instant. So now if you apply Kirchhoff's voltage law to this loop, you can see that you get an equation like this. So if you start from this point, we are meeting a rise in potential, so it is Vs. So you can see that there will be a drop across this, and that drop will be given by, and you can see that as the current is flowing in this direction, it will have a drop with these polarities. That means you are meeting a rise in, a fall in potential, so that will be given by Is. All these terms are in, all Vs and Is all are in phasors. And here it will be R plus Jx, which is the impedance there, and at this point you are meeting a drop in potential, so the equation will be minus Vr equal to 0, or it will be Vs will be equal to Is into R plus Jx plus Vr. So this will be the equation representing this network, and it can be represented as a phasor diagram. Here you can see that Vs, this is the Vs, sending end voltage, and the voltage at the receiving end will be represented as Vr as the receiving end voltage. So Vs is the sending end voltage and Vr is the receiving end voltage. So Vs, the sending end voltage, will be given by Is into R plus Jx, where Is is the sending end voltage. And in this case you can see that Is is IR itself, because the same current, there is no shunt element here. So Is will be the same as IR. From this representation of the short transmission lines, the phasor representation of various variables can be drawn like this. Here the receiving end voltage IR, and in this case you can see that IR is the same as Is, the sending end current. IR is the receiving end current. The phasor diagram can be drawn like this. If you take IR as the reference phasor, you can see that Vr will be leading, because in this case you can see that the current will be lagging with respect to the terminal voltages. And you can see that here we are considering only the transmission line. Actually we will be connecting a load across this, across the receiving end. But in this particular circuit you can see that Vr will be leading with respect to IR, or IR will be lagging with respect to Vr. So Vs, Vr and IR can be drawn like this. We are from the phasor diagram, from the application of the Kirchhoff's voltage law for this particular loop as shown in this figure, you can see that the resultant equation will be Vs is equal to Is into R plus Jx plus Vr. All these quantities are phasors. So Vs can be written as Is, and here Vr, and this is the IR drop. You can see that IR into R, the resistive drop will be in phase with IR. That is why it is drawn parallel to this phasor. So VR plus IR, this is the IR into capital R, that is the resistive drop, and this is the reactant, the drop due to the reactance. And you can see that it will be leading by an angle. This is a voltage drop across the reactance, so it will be leading with respect to IR by an angle 90 degree. That is why it is shown like this. And in fact, you can see that the drop across the impedance, say R plus Jx, will be this one from here VR to here, and its components are IR into capital R plus J into IR into capital X, where X is the line reactance and R is the line resistance. So VR plus this drop is the drop across this impedance R plus Jx, that will give you Vs. In order to estimate the value of the sending end voltage, we can write the equation. Here you can see that this, if you consider this right angle to triangle from this point up to here Vs, and from here, say for example a triangle ABC, if you consider AC square, which is equal to Vs square. So this can be written like this: Vs square is equal to, here Vs square will be equal to this square, that is or it can be taken AB square plus BC square. AB square is, here you can see that AB square will be VR. If you project this along the, or the component of this phasor along the x-axis, it will be VR cos phi r, because this angle is phi r and this angle is phi s. So this distance from A to this point, it will be VR cos phi r, plus this is IR into capital R. So V square will be equal to VR cos phi r plus IR, this whole square plus this you have to consider. And you can see that this distance will be the projection of the phasor VR on the vertical axis or on the y axis, and it will be equal to VR sin phi. This distance will be VR sin phi, plus this is IR into x. So VR sin phi plus IRx, that is Vs sin phi. And you can see that Vs square will be equal to this square plus this square, or it can be written like this. Here you can see that Vs square is equal to, so it can be written like this: Vs square is equal to, right here, AB square plus BC square. And that is equal to, AB square is VR cos phi r plus IR into R. VR cos phi r plus IR into capital R, this whole square, plus this is VR sin phi r, this distance, plus IR into x, VR sin phi r plus IRx. And from this you can estimate the value Vs square, that will be equal to, here you have VR cos square phi r, VR square cos square phi r plus 2 VR IR cos phi r into R, plus I square R, IR square R square, plus expansion of this, that will be VR square sin square phi r plus IR square into x square, plus 2 VR sin phi r into IR into x. And here you can see that VR square phi r square plus VR square cos square phi r plus VR square sin square phi r, that will be equal to VR square, plus here you have IR square into R square plus x square. plus it will be like this: VR square plus IR square R square plus 2VR IR into R cos phi R plus X sin phi R. And here you can see that this is the expression what we have obtained: Vs square is equal to VR square plus 2 IR R VR cos phi R plus this term plus IR square plus R square X square. From this you can see that Vs square, if you take VR outside, here VR can be taken outside. So Vs square will be equal to, say here it can be written as VR square into 1 plus VR square we have taken out. So you have 2 IR into R cos phi R by VR, this term. And similarly here you have taken the VR outside. So you have 2 IR. So you have plus 2 IR X sin phi R by VR, and here IR square into R square plus X square by VR square, and we are taking the square root. So on the left hand side you have Vs. So Vs is equal to, here if you take the square root of this, the expression will be Vs is equal to VR into 1 plus this expression. And you can see that this can be written in the form 1 plus X raised to N, because here this can be Vs is equal to VR into, say VR into 1 plus some expression raised to 1 by 2. The last term is VR square IR. Here you can see that IR square plus R square, that is the drop across this, because here you can see that IR into Z is actually root of R square plus X square, and so if you find the voltage drop across this, that is square of the voltage drop across this, it is IR square into R square plus X square, that divided by VR square, the receiving end voltage. So compared with the receiving end voltage, the drop across this impedance will be very less. So the ratio between the voltage square, or the ratio between the drop across this impedance and the receiving end voltage will be always less than 1. So as an approximation you can neglect that term. So finally you can see that Vs will be equal to VR into 1 plus this expression raised to half. So it is of the form 1 plus X raised to half, and you can see that this term will always be less than 1. So this can be written in the form Vs is equal to VR into, say here 1 plus some term X raised to, say 1 by 2, and it can be expanded as an infinite series. It will be 1 plus nx plus n into n minus 1 by 1 into 2 x square, and it's an infinite series. So if you consider only the first term will be 1 and the second term will be nx, and here n is half, that you might have studied in the mathematics. So if you consider only two terms, it will be 1 plus nx. So here n is half. So if you multiply this with this term, this 2 and this half get cancelled, and you have IR into capital R by VR into cos phi R, this term, divided by IR into capital X by VR into sin phi R, and you have a VR outside here. So if you expand, this VR and this VR get cancelled, and finally you will be getting the sending end voltage will be approximately equal to VR, the receiving end voltage, plus IR into capital R cos phi R plus IR into X sin phi R. Here capital R is the line resistance and capital X is the line reactance, and phi R is the power factor angle as shown in this figure. Phi R is the phase difference between the receiving end voltage and the receiving end current. And at no load, the receiving end voltage will be the sending end voltage itself. That is quite clear, because when there is no load on the transmission line, the sending end or the receiving end voltage will be equal to the sending end voltage, because there won't be any voltage drop. And you can see that at no load receiving end voltage will be the sending end voltage. So at no load the receiving end voltage is Vs, so you can substitute that here, and the regulation is from the definition, the difference between the no load and the full load voltage expressed in terms of the, or expressed as a percentage of the rated voltage. Here for the, as far as receiving end voltage is concerned, this is the no load voltage. So Vs minus VR by VR will give the regulation. So from this formula you can see that Vs minus Vr will be equal to IR into capital R cos phi R plus IR into X sin phi R. So that expression Vs minus Vr, which is equal to this divided by Vr into 100 will give the percentage regulation. And so this is the formula for the percentage regulation or per unit regulation. Here you can see that IR into R, this will be having the same unit as that of the voltage, and here also this is also in volts. So regulation per unit, it will be IR into R by VR cos phi R plus IR into capital X by VR into sin phi R. Here you have to remember that R, the suffix R indicates that it is the receiving end current and voltages, and phi R is the power factor. Capital R and capital X are the respectively the line resistance and the line reactance. So this formula you have to remember. And if you consider the transmission parameters, you might have studied this in the network analysis. In case of a two-port network, you have two set of parameters. If you consider this two-port network, you have four parameters I1, V1 with these directions as indicated. I1 will be flowing into the network, and this is the voltage across the first port. And here you can see that I2 will be flowing into the network here. And as far as the transmission line is concerned, you can see that IS will be, or the sending end current will be flowing into the network, and IR will also be flowing and IR will be flowing out of the network. So if you compare these two-port networks, here you can see that for the standard two-port network representation in terms of its transmission line parameters, the standard equation is this: V1 I1 is equal to ABCD. These ABCD are the ABCD parameters or the transmission line parameters, and V2 and I2. Here you can see that these are the dependent variables and these are the independent variables. And here you can see that this formula is actually derived from this network, and you can see that in this case I2 is equal to minus I2 will be, here you can see that I2 is flowing into the network, so minus I2 will be flowing out of the network. So here you have minus I2 in the standard formula, so this minus I2 will be equal to IR in this case. That you have to remember if you compare the standard two-port network from where we have formulated, or from where we have derived this expression for the transmission line parameters. So in order to represent the short transmission line in terms of their transmission line parameters, the standard equation will be this: V1 and I1 will be Vs and Is, the sending end voltage and sending end current respectively, and A, B, C, D are the transmission line parameters. And instead of V2 and I2, you have VR as the receiving end voltage and IR as the receiving end current. So the formula here, from here you can see that V1 will be equal to AV2 minus BI2, and here instead of minus I2 we have IR, because IR is flowing out of the network. So if you represent this two-port network in terms of the parameters, the equations will be, say, V1 I1, which is equal to the sending end voltage Vs and Is, and you have the ABCD or the transmission line parameters ABCD like this, and you have the receiving end voltage VR here and IR there. You can see that IR is flowing out of the network, that is why this negative is replaced with this. So you have to remember this formula. And from here V1 is equal to, here V1 is the voltage and current corresponding at the port 1, and V1 is Vs here, and I1 is the current flowing into the network at the first ports, so that is Is, the sending end current. That will be equal to, say, ABCD, the matrix ABCD, which represents the transmission line parameter, and here you have VR IR. So from this formula, from the standard representation, the formula will be Vs is equal to AVR plus BIR, and Is is equal to CVR plus IR. That means if you represent the sending end voltage in terms of the receiving end voltage and receiving end current, from that formula you can evaluate the transmission or the ABCD parameters A and B, the transmission line parameters, and from the if you can represent the sending end current in terms of the receiving end voltage and receiving end current, you can evaluate C and D. So once you get A, B, C, D parameters, you can represent the transmission line in terms of its transmission or ABCD parameters. So from here we have seen this is the standard representation. So if you consider the ABCD or the transmission line parameters of the short transmission line, it can be written as, say, VS, sending end voltage, the sending end current IS, that is equal to, say, A, B, C, D. These are the transmission line parameters, and here you have VR and IR. And this yield the equations VS is equal to AVR plus BIR. That is the first formula. Second one is 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 equal to CVR plus DIR. And from the equivalent circuit of the transmission line, here you can see that this is the governing formula. VS is equal to IS into R plus JX plus VR. So if you write it here, VS is equal to IR into R plus JX plus VR. This is the formula. So if you compare these two formulas, actually you have to represent VS in terms of VR and IR. So here you have VS in terms of VR and IR. This is the formula, and in this, from this formula you can see that IR is the same as IS. That is why I have taken, instead of IS, IR here, because from the equivalent circuit you can see that IR is equal to IS. So if you can represent IS in terms of VR and IR, you can get C and D. And if you compare these two equations, here you can see that IS is in terms of VR and IR. Here the coefficient of VR is 0. So if you compare this, here you can see that C will be equal to 0 because the coefficient of VR in this expression is 0, and D, the coefficient of IR in this expression, that is 1. So D is equal to 1. And from here you can see that VS in terms of, so if you compare the coefficient of VR in this expression, the coefficient of VR in this expression is 1. That means A is equal to 1, and the expression for B is actually the coefficient of IR in this expression. So coefficient of IR in this expression is R plus JX, which is the impedance, say, Z. So B will be equal to Z. So the transmission line parameters of the short transmission line is this matrix. A is equal to 1, you have B is equal to Z, which is given by R plus JX, and C is equal to 0 and D is equal to 1. So this matrix will represent the transmission line parameters, or the ABCD parameters of the short transmission line. So that also you have to remember. Question may come to derive the expression A is equal to 1, B is equal to Z, C equal to 0 and D is equal to 1 for a short transmission line. Here we can compare that A is equal to 1, B is equal to Z, C is equal to 0 and D is equal to 1 in this expression, and that is the transmission line parameters of the short transmission line. And the percentage efficiency will be given by power received at the receiving end divided by the power received at the receiving end plus losses. Here you can see that the denominator represents the sending end power, because the receiving end power plus the losses will give you the sending end power. So this ratio multiplied by 100 will give you the percentage efficiency of the short transmission line. Here you have to remember that R is the resistance per phase of the line, because you can represent the three-phase line in terms of the equivalent single phase representation or per phase representation.